Hello everyone, my name is Yihui Xu from Suzhou University. It is a great honor to present our work, evaluating terminology translation in machine translation systems via metamorphic testing. This project is the outcome of a collaborative effort between researchers from Suzhou University and Nanjing University, including my co-authors Yanhui Li, Jun Wang, and Xiaofang Zhang. Next, I will outline the structure of my presentation. We begin with the introduction, where I will provide the background and motivation driving our development of TermMT. Following that, the method section will offer a detailed process of how TermMT operates. In the evaluation section, I will present key research questions and discuss our experimental findings. Now, we turn our attention to the introduction. In this section, I will provide an overview of the background and motivation that underpin our study. Despite significant advances in narrow machine translation, errors remain an inevitable issue. For instance, Google Translate has mistakenly translated "besting in progress" as "workers exploding," which can lead to severe misinterpretations. Additionally, machine translation errors are more frequent than those found in human translations, potentially resulting in serious consequences. To address this issue, existing studies have highlighted the necessity for rigorous testing of machine translation systems. These studies employ input mutations and metamorphic rules to evaluate system consistency and robustness, aiming to enhance translation quality. According to general terminology theory, a term can be distinguished from words in ordinary language by its single meaning relationship with a specialized concipit. In various fields, terminology serves as concipit labels, and their translation accuracy is crucial for overall translation quality. For instance, if the term "part of speech" is incorrectly translated as "part of pronunciation," it alters the original meaning entirely. This highlights the significance of accurate terminology translation, as even minor inaccuracies can lead to major misunderstandings. In addressing the limitations of current terminology testing, we recognize the heavy reliance on reference translations and bilingual dictionaries, which significantly limits the scale of automatic testing. To overcome these challenges, we propose TermMT, a metamorphic testing approach designed to detect terminology translation errors. The core idea behind TermMT is the design of metamorphic relationships based on the inherent properties of terms. These MRs enable us to systematically identify errors in both immutable and mutable term translations. Having addressed the limitations and motivations behind our research, we will now proceed to discuss the methodology employed in our study. Moving on to the overview of TermMT, our methodology consists of 4 key steps: preprocessing, mutation, translation and alignment, and error detection. In the preprocessing phase, we focus on constructing a comprehensive term dictionary. We draw upon reliable sources including Wikidictionary and the IAT datasets to extract relevant information, including non-meanings, synonyms, part of speech, and Chinese translations. This process also involves manual grammar corrections to ensure accuracy, automatically resulting in a final dictionary comprising 4,518 multi-word terms. Additionally, we collect sentences for mutation by announcing an English corpus to identify sentences that contain these multi-word non-terms. Importantly, we exclude sentences that exceed 50 tokens to maintain clarity and relevance in our dataset. Now, let us delve into the first mutation technique, meaning insertion. The primary goal of this process is to integrate the meaning of a multi-word term directly into the sentence. To accomplish this, we employ FLAIR for part-of-speech tagging to accurately identify the context of the terms. We then extract the corresponding meanings from our constructed dictionary. To select the most suitable mutant, we adopt the BGE model, which helps us choose the mutant with the highest cosine similarity to the original sentence. For instance, considering the original sentence, the term "part of speech" is, in our mutated version, we insert the meaning to create the term part of speech Grammarly category is. Next, we explore mutation 2, term partial replacement. The goal here is to replace part of multi-word term with a different word. We adopt the BG model to generate masked sentences, replacing specific terms with nouns that lack shared roots or synonyms. For example, the phrase part of speech is transformed into system of speech. After completing the two types of mutations, we translate the original sentences and the two kinds of mutated sentences. Next, we align the source sentences and their translations using the pre-trained alignment model to extract the translation results of the terms within the sentences. As shown in the illustration, the aligned results are marked in bold. In our approach to error detection, we employ three metamorphic relationships. Firstly, MR1 stipulates that the translations of terms in the original sentences and meaningization must be consistent. Secondly, MR2 states that the translation of meaningization sentence should align with the original, excluding the inverted explanation. Lastly, MR3 requires that the translation of terms in original and partial replacement sentence must differ in translation. To mitigate false positives, we incorporate a GPT filtering process. This involves verifying whether the inverted meaning align with the context, ensuring that term translations between the original and mutated sentences are consistent, and confirming that the original and mutated sentences can't be translated to the same Chinese term. As we move forward, we will delve into the evaluation phase, focusing on our research questions and discussions regarding the findings and implications of our work. For our evaluation, we use the English portion of the CROPS. This dataset encompasses various professional fields, including subtitles, science, laws, news, and academic. By selecting these domains, we ensure that our findings are relevant and applicable to specialized contexts. Now, let's move on to our research questions. RQ1 addresses the correctness of our mutated sentence generation. RQ2 focuses on the effectiveness of our method, TermMT, in detecting translation errors. RQ3 examines the impact of the similarity threshold on our approach. RQ4 compares TermMT with the state-of-art methods. Finally, RQ5 evaluates the efficiency of TermMT in terms of running time. Let's delve into our first research question, RQ1, correctness of mutated sentences. In this section, we aim to determine the realism of the mutated sentences generated by our method. To evaluate this, we randomly selected 500 test cases, which included both types of mutations we explored. Our findings indicate that both types of mutations are capable of producing a significant portion of realistic sentences. In RQ2, we evaluate the effectiveness of our method in detecting translation errors across various machine translation systems. We conducted an extensive error detection analysis on the evaluation dataset and select 900 errors at random for manual verification. The results highlight that our method is capable of identifying a significant volume of translation errors across three types of machine translation systems with high levels of precision. Now, we will turn our attention to RQ3, which investigates the impact of similarity thresholds on our methodology. In this section, we analyze how different similarity thresholds influence our results. Our dataset comprises 900 results, diverse from 3 narrow machine translation systems and 3 MRs. The findings indicate that the choice of similarity thresholds significantly affects both the number and accuracy of detected translation errors. Next, we will examine RQ4, which focuses on the comparison between our proposed method and existing state-of-art translation error detection techniques. Our analysis reveals that TermMT detects a comparable numbers of translation errors when compared with the existing method, CAT. Furthermore, our approach identifies many unique errors across various datasets. showcasing its effectiveness as a complementary approach to existing error detection methods. Finally, we address RQ5, which focuses on the efficiency of our method in terms of running time. In total, the average running time for our approach is 3.37 seconds per original sentence. In this final section, I will outline the key discussions that emerge from our findings. Discussion 1 focuses on the overlaps between the metamorphic relationships we employed and the models studied in our research. Discussion 2 highlights the contributions of GPT to enhancing accuracy within our methodology. Discussion 3 examines the performance of different language model settings when calculating similarity. Discussion 4 contrasts our approach with reference-based methods. Discussion 5 delves into how TMMT functions as a translation testing framework for large language models. Discussion 6 presents the translation errors reported by TMMT. Finally, Discussion 7 offers insights of our study, suggesting directions for further research and improvement in terminology translation testing. Thank you very much for your kind attention. I would like to express my heartfelt gratitude to my collaborators from Suzhou University and Nanjing University. I welcome any questions or feedback you may have.